top of helpful on top.
No, yeah, I'm sure it will be. I mean, again, just all sorts of additional pointers and practice problems and everything will be helpful. So from your emails, it sounded like arrow pushing or that whole sort of like arrow notation was a big sticking point. Can I give you just a few quick pointers on that before we get into specific questions?
That sounds good.
Okay. All right, so I'm going to share my screen with you so so I can work through these. Give me 1 second. Let me get ready for that. Where are we? Fall, this. Awesome.
Because I remember you had stated in your video, and I had heard that section multiple times, where it's like the number one thing that you want us to really get used to, that way we can determine more easily what resonance structures there are, is to find all those quote illegal moves.
Yeah, totally. And even more so, let's just like real quick review what we're doing when we're doing this whole arrow pushing business, because I know it's new to everybody. So let me just so first of all, hopefully you can see my screen now.
Yes, sir.
Okay, so let's just do an example here. So I'll just tell you right off the bat that this compound does have resonance, right? So actually taking a step back, there were 3 resonance videos. The first one sort of introduced you to this arrow pushing notation, okay? The second one was all about being identify one of those 5 classes of molecules that have resonance, right? So being able to see a pattern in a molecule and knowing, okay, that has to have resonance. That was that second video. And then the third one was delocalized versus localized electrons. I think the first 2 are probably the hardest. So that's what I wanted to go over. So let's just point out here that this is indeed a molecule that has resonance, and it's because it has a pi bond, right? So double bond here between atoms of differing electronegativity. Oxygen's more electronegative than carbon. Yeah. So the resonance structure that we have for this one looks something like this. This pair of electrons jumps up here, and we get a structure that looks something like this. Actually, let me be good and draw my dots on this one too. So one of the things that I want to point out is what exactly we're doing when we're drawing our arrows, right? So it's called electron pushing kind of for a reason. What you want to think when you're drawing these arrows is you're literally grabbing a pair of electrons that was originally in this bond here and moving it up to that atom, in this case, oxygen. So this pair of electrons that was in that pi bond is now this lone pair here, okay? The other super duper crucial thing to remember about resonance is our electron pushing is electrons have negative charge, right? So when we're moving electrons around, you're almost always going to have to consider charges. So if we had that formal charge video where we were, which was all about patterns, so maybe you can notice based on that video, we have 3 lone pairs and 1 bond on this oxygen. So what should the formal charge be? Do you know?
So with the 3 lone pairs and the 1 bond, it would, and oxygen usually having what is it? A stoic number, right? No.
So oxygen wants to have 2 bonds and 2 lone pairs. So if it ever breaks that pattern,
it would be -1.
Yeah, so if it ever breaks that pattern, you know it's going to have a formal charge. In this case, absolutely 3 pairs of electrons and 1 bond, that'd be a charge of -1. The other thing that's really important to remember is conservation of charges, right? So this is one thing that I said in the video that I kind of wish I had stressed a little bit more, is that you should have the same net charge over here as you do over here. Yeah. So the net charge on this side is 0, right? I have no charged atoms. So that means if I have a -1 charge over here, it has to be balanced by a positive charge. In this case, it would be on that carbon. And you can sort of hopefully see that was when I grabbed this pair of electrons that used to be associated with this carbon, and I took it away from it. You know, I like snatched it and put it on that oxygen. So that's why it's left with a positive charge. But one of the things that you can always do to check your work is make sure that you have the same net charge on both sides of your equation. If you start out with a positive charge, you should have a positive charge at the end. Start out neutral, everything should at least add up to be 0 at the end. So that's like one quick check to do. Cool? Okay. So that's just like the simple basics of electron pushing that I kind of wish I had maybe stressed a little bit more. So now we can get into like your particular problems here. So were there any specific questions that you had? I mean, I know there were a few.
There definitely are a few, but
Okay.
to jump onto the one that I have right there, with that structure, right? You had talked in one of the videos about the resonance contributors, and then like the statistical probability that one will be more likely to contribute than others when it pertains to like how, on what percentage of these structures.
But to be clear, you're not going to be quantifying anything. You should be able to look at this and tell me this one's more stable than that one, but you shouldn't be able to give me like a 90%, 10% or something like that. Okay, cool. I just wanted to make sure that that was.
No.
Yeah, so certainly one of these. I mean, yeah, so certainly one of these resonance contributors is more stable than the other one, right? So do you have an inkling as to what one that would be?
Well, as far as I remember from the video, the positive carbon cation with the 3 hydrogens was the least of all stability, and the one, and also having a charge. I remember you mentioned just simply the fact that one has a charge and that both atoms now have a formal charge in the ladder makes them unstable.
Yeah, so actually that was having to do with all, like if you're comparing carbocations. So for example, a tertiary carbocation is going to be more stable than a secondary carbocation, more stable than a primary carbocation. But nonetheless, one thing that you should always keep in mind is this idea that like atoms don't like to have a formal charge. So anytime you have an option of, for example, this structure here where nobody has a formal charge versus this structure here where both atoms have a formal charge, this is going to be less stable. And it doesn't mean that it's irrelevant, right? I mean, it still is very important for the chemistry of this particular functional group, but nonetheless, it's just not going to be the dominant contributor.
So it's not a quote a dominant contributor, but even it is a statistical probability that exists, so it is marketed as a resonance structure.
Yeah, so anytime any resonance is available, even if it's like a relatively unstable contributor, it's still significant to the chemistry of the molecule. So for example, this carbon has this like sort of like partial positive charge. It will see that it's susceptible to attack from things that have, I can't think of something off the top of my head. It's going to be susceptible to attack from something with like a negative charge is one of the examples that we'll see. So anytime you can draw resonance structures, anytime something fits into one of those 5 categories, I think it's on slide 40 of chapter 2, it's something to keep in mind. It's something that will be important for the chemistry of the molecule, even if it's not necessarily a dominant contributor. So we still care about resonance structures even when they're not dominant, even when they're less stable, like in this case. It's still something that's important to note.
Okay.
Right. And what exactly it means by like important to its chemistry, we just haven't gotten there. We'll see when we start talking about ketones and stuff, what I mean by that. But yeah.
So one of them had mentioned one of the categories of like how to like your organic chemistry for dummies cheat sheet for recognizing potential resonance was a lone pair next to a positive charge.
Yeah. So we could. I'll just draw that quick.
This isn't really like related to any problem I had, but it's just related to like a question that I had regarding it. Why is it only a positive charge and not the antithesis? Why is it near a negative charge is a negative charge not shift around also, or?
No, the negative charge will. So both of these structures have resonance. The difference is that this one would require 1 arrow to draw its resonance contributor, whereas this one actually requires 2. It would be this guy coming down and this one having to come up here, because otherwise carbon would have too many bonds. So the other
Okay.
resonance contributor here, let me just draw it out, would be this guy with the positive charge. And then this would have that negative charge over there. So both, if you have a charge,
that would be that would be covered by the Lilith lone pair, right? It's a lone pair that's one adjacent to a double bond, a pi bond.
Yeah, so first of all, it's important to recognize that if you have a charge in this allylic position, there's resonance, boom. But allylic lone pairs, these will be 2 arrows if you look at the cheat sheet. And this one, when you have an allylic positive, it will be 1 arrow. That's really both of them have resonance. It's just trying to hammer home how many arrows you need to make sure to draw.
Okay.
Right, and again, I guess just to point it out.
On that same molecule. No, continue. Sorry.
Just to point out why you have to have the 2 arrows. So again, something to remember about electrons, right? They're not like marbles that you're flicking around. They're these clouds, so they can sort of like move and simultaneously together. So in this case, you have to have the 2 arrows, because if you just drew the 1, the result would be, right? So let me just be clear. If I got rid of this one here, the result would have like 2 bonds and this lone pair on this carbon. You just got too many bonds going on. So you have to make sure to draw that second arrow at the same time. These jumps are happening simultaneously.
Okay. That answers actually one of my questions. I tried to clarify, but I clarified in a manner that actually didn't clarify my question at all, because I was asking the wrong question, which I did later realize. But I had asked, all the moves have to be legal in all steps, and I had this misconstruction where it's like, I guess that example functions just fine. Where that lone pair was down there, in my mind, I was like drawing step 1, the lone pair goes up, step 2, the bond breaks and goes over there, and then that whole thing would be, quote, a bad move, because at that one point there would be the 4 bonds and a lone pair there.
Yeah, sometimes you can think about it as happening step 1, step 2, step 3, and that's way simpler for our minds to digest, so we tend to go there. But again, with electrons, these things can be happening simultaneously. So sort of exactly what you said. If you can do them step by step, but no move is quote unquote illegal, then that's fine. But there are totally things where they have to be done simultaneously. This jump happens at the same time as this one in order for us to avoid those illegal moves.
Okay, to expand on the one on the molecule on the right.
Okay.
If in the hypothetical situation, it was like literally mirrored with the same, so pretty much a double bond coming off the end of the right-hand side, would it then have it'd have multiple resonance, right? One going to the right and one going to the left.
Something like this.
So you double bond, single, the lone pair, single, and then a double bond.
Yeah. Oh, okay. So now I got one more carbon going on, you're saying?
Yeah, no, it's adding to it. It's obviously a completely different molecule.
This guy right here.
That confused me there. Like, is there only 2, or am I missing something where there is more than just?
No, so here, this is a really good point. So here, there are multiple resonance structures, and you can't actually draw them all in one shot. So there's the one that we had before. This guy comes down there. This guy comes up there. So that takes me here. There's also just a completely other one available. I'm going to use a different color to try to stress that, which is sort of the mirror image here.
Yeah.
Okay, so you don't have to like be able to draw them all in one shot and that's the only ones available. You can, we're going to see cases where you actually have conflicting resonance structures where one kind of leads to one kind of chemistry and the other leads to another kind of chemistry and all that other jazz. So in this case here, this would be the situation. You have two different paths for this particular arrow. And then of course, because everything's complicated in quantum mechanics, all of these have to be considered together as being like, again, that whole nectarine example. Yeah, they're all true at the same time, exactly.
Okay, so that makes sense. And then from that, there's no more, because now isn't that, if that that lone pair were to move, it would just end up back in the center, right? It wouldn't
yeah, totally. So yeah, I can do the reverse. You should always be able to get your original structure back, right? So then I could do this to here and I would wind up back there, and then the other jump to get to the red one, etc.
I ran into like a immediate speed bump when we were I was dealing with the same structure where it was 1, 2, 3, and then on the third bond was a nitrogen with a lone pair, and then on the second was a double bonded oxygen.
Yeah, okay. So actually, this is I think you're talking about this.
Yeah.
Okay. These are actually one of the functional groups that you should be able to recognize too. So hopefully, just to sort of quiz you on that, like hopefully that's something you remember from the functional groups. This is an amide. Okay. And yes, absolutely. So this is, again, this allylic lone pair pattern.
Yeah.
Okay. So sorry, what was your specific confusion?
So I know there should still be resonance ignoring the nitrogen with the pi bond, right? Going up to the oxygen and making the oxygen negative and the carbon positive, right?
Yep.
Then there's a lone pair next to a positive charge.
Yeah, totally.
So wouldn't from there the lone pair migrate over there, or am I not? Am I like then turn into a double bond, or am I missing?
No, yeah, you're absolutely dead on, right? So if I'm going to do this first step, I get this, and now I have this lone pair next to this positive charge, so that can come down here. And so where, again, conservation of charges, am I done here?
No, the nitrogen has 4 bonds, so it have a formal charge of 1.
Yep. Yep, so absolutely. These are definitely 3 resonance structures. Let's try to rank these real quick in terms of stability. Which one's going to be the most stable resonance contributor?
The original.
Yeah, right. So always the one where there's no formal charges. That's always going to be the most stable. Out of these two, let's call them 2 and 3. Which one do you think is the more stable one?
Three.
Yeah, absolutely. Why is that?
I believe it's because it does a better job of spreading out the charge.
Well, so really the 2 is carbon has only 6 electrons in its octet. So both of them have 2 formal charges, right? A -1 and a +1. On number 2, though, carbon has only 6 electrons in its octet, whereas in number 3, at least everybody has a full octet.
Yeah, even though
so that's why 3 would be a little bit, I mean, not like that much better, but yeah, a little bit better. And in fact, when we talk about amides, we actually won't until next semester, but we'll see that this resonance structure plays a big role. This bond right here doesn't really rotate because of that resonance structure. So anyways, yeah, again, I know it seems like a little weird that we're going through and drawing all these different resonance structures, especially when we're going to say they're less stable than the original, but again, it's because they do still have an important impact on the chemistry.
Yeah, but and like I mean, like the biggest thing I've learned from chemistry is if anything's statistically probable, that means it happens eventually.
Totally, absolutely. And I mean, right? I mean, you're talking about the speed of electrons move. You're talking about like femtosecond type behavior here. So yeah.
All right. So then the next thing I was really confused about, and maybe I was just misconstruing like what was being said, just because like 50 things before I got to it confused me, so I just immediately determined that was confusing too.
Yeah, no, that's what happens in chemistry, unfortunately.
When you're talking about delocalized electrons, what does that like actually mean? Because
so if they're, yeah, go for it.
I was gonna say, like, I know obviously delocalized means not in its original place, and electrons are electrons, but like
yeah.
when I'm looking at these like resonance structures, what's the connection to, and how do I count them?
Yeah, totally. Okay, so actually let's take this amide example again, but I'm going to make it a little bit different. Okay. So we have our resonance structures that we just drew for the amide, right?
Yeah.
But now I have this other double bond over here, right? I put that in there strategically because it's too far away to actually be participating in any resonance, right? If it was right next door to this pair of electrons, then sure, but it's just too far away.
Yeah.
So this is an example here of a localized pi bond. Its electrons can't participate in resonance, so they're just stuck where they are. Exactly what you said, right? I mean, that's the one thing you want to tease out. These vocab words aren't that difficult. Delocalized, meaning it's not staying in the same place. Localized, meaning it is. Yeah. So delocalized means that it's participating in resonance. Localized means that it's not. All sigma bonds, let me just state this outright. All sigma bonds are localized. So when I was asking you about localized electrons, I was specifically asking about pi electrons, because if I'm asking about all electrons, all sigma bonds are all localized. So that's not the interesting one. I want you to be able to distinguish between which pi electrons are delocalized and which ones are localized.
So in this example, the ones on the oxygen double bond would be considered delocalized?
Yeah, so not only, so this pair right here is delocalized. Delocalized.
And then so would the lone pair on the nitrogen?
Absolutely. So all those electrons that are participating in resonance are delocalized. One of the things that I realized after I made the assignment is I should have also asked you about localized lone pairs, because you should be able to spot which lone pairs are localized and which one are delocalized. I honestly just didn't think to put that in the assignment, and that was my bad. But yeah, so the difference, right, in terms of localized pi bonds, and actually I think I asked you about localized pi electrons. Yeah. So then you'd have to remember that there are 2 electrons in every bond.
That led up to the next question, because that felt like asking a math professor what 2 + 2 was, but at the same time, it was like I said, it was literally 50 confusing things leading into this thing that seems like it should make sense, but because it made immediate sense, it feels like I'm wrong.
No, yeah, that's one of the things about chemistry. I hope everybody can sort of grasp it, especially about this course, is we're just going to build and build and build. Like if you're confused about step 1, you're pretty much screwed for step 2 through 5. You know, so that's why, like, I'm always hammering home that I'm like available on Zoom, because yeah, hit me up. Let's get that confusion all cleared out. Otherwise, you're going to spend 2 hours watching lecture videos that you don't understand. You know, it's like, it's better to just get it all cleared up, because then you can build off that foundation. So absolutely. I mean, if resonance 1 and 2 were confusing, resonance 3 is going to be super confusing, as well as I just want to throw it out there that resonance is very confusing to begin with. So
So to answer the question that wasn't asked, that you said you would have asked, the two lone pairs on the oxygen that are generally always there, would they be considered localized?
They would, yep. So you're absolutely right. Here we got, so if we were gonna like do the full litany of what I could ask you about this molecule, I could ask you number of delocalized electrons, number of localized lone pairs, and localized, whoops, getting sloppy, pi bond electrons or pi electrons. Let's actually use the same language I did in the quiz, just so we're not confused. Localized lone pair, what do you even will say? Localized lone pair electrons. All right, and then we'll even do sigma bond just to do sigma bonds, okay? So if we're gonna fill all this in here, how many delocalized electrons did I have?
Delocalized electrons were just for this, the two on the nitrogen. And
so not only
the two in the bond, in the, the double pi bond.
Right. So that means four electrons are delocalized, right? We got a pair on the lone pair and a pair in a pi bond, so that's 4 electrons. So then how many localized localized lone pair electrons? You had said it before, that would be the 4 on the oxygen. Yep. So, and I guess we can even color code this so that it's super duper clear. When I'm talking about my 4, I'm talking about those. And then what about localized pi electrons?
It would be the pi bond that's too far away to actually contribute to the.
Yeah, and again, I just want to point out, make extra special clear, this guy's sp3 hybridized. That's what F's everything up, right? If you have an sp3 in the middle, that's what's going to mess you up. So absolutely, this would be 2 localized electrons.
Okay.
And then sigma bonds is actually kind of a pain in the butt, because of course we have the ones that we can specifically point to here. 1, 2, 3, 4, 5, 6, but right, that's not all of them, correct?
Yeah, then there's all the hydrogens attached to the butt end of everything else.
Yeah, exactly. So this is when you have to remember how your bond line structures work and go in and fill in everything with how many it should have. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 sigma bonds. I'm double checking now. I'm pretty sure that's correct.
Okay. It didn't really have it as an example in the discussion, but is there ever a time where those conjugate bonds, so the ones that are made into a ring, where those will actually delocalize out of the ring?
Oh yeah, so sure, absolutely. So let's just take, so first of all, benzene, right, is this classic delocalized pi bond electrons. But yeah, if you had something like this, those electrons would absolutely also delocalize outside of the ring. Importantly, right, because I have that perfect spacing of 1 sigma bond in between. If I had something like this, these electrons would not delocalize outside of the ring, again, because I have an sp3 hybridized molecule messing it up, right? One of the key things to remember about resonance is it occurs because of those p orbitals that are sticking sort of perpendicular to the frame of the molecule. So absolutely, here, every single one of these along the way are all sp2 hybridized, meaning they have that leftover p orbital. And so yeah, these electrons will delocalize outside of this ring. You can even have like rings that are back to back to one another.
And it'll just, if they're, I mean, like this in.
So I mean like something like this. These electrons are all delocalized in this system here.
Okay. Let me find a good example of the question that I have there.
Yeah.
That isn't
take your time.
directly. So if when in these resonance structures it shows like a molecule and then the hydrogen above it and there's a plus next to it, that plus relates to the molecule below the hydrogen, right? Or does it refer to the hydrogen itself?
I'm not too sure what you're, so maybe if I'm wrong here, let me just, then I'm not too sure, but I think maybe you're talking about something like this.
Yeah.
Okay, so this is the particular molecular drawing program that I use. Anytime you put a charge on a carbon atom, it does this. To be honest, you will, if I didn't use that special program, like your book would probably just show you this. And these are the exact same thing. But yes, the charge is not gonna correspond to the hydrogen. If there was a charge on the hydrogen of +1, it would be all by itself as a proton.
Yeah.
Right? Like we'll see this when we talk about acids and bases, but if you remember, acids give protons.
Yeah, and then they just kind of float around in solution.
Absolutely, right? So this charge has to be associated with that carbon, not that hydrogen. But it's honestly a little bit of an anomaly because of the program that I use. I wish it would do this, but it doesn't.
Okay. Yeah, that was just kind of a clarification question, because I was like, when looking at it, it makes sense that it's supposed to be on the carbon, but then it's also on the hydrogen, and then it was probably, again, one of those things where it's like 50 things before this were confusing. So yeah, no, this is just confusing.
Yeah, and it's a good pattern to spot, because again, that's the program that I use. So you'll probably see it like that a lot. But it is important to note that these are the two of the exact same. These two are sort of different representations of the exact same molecule.
Okay, and then in that example, which is a good example, is there any resonance there? It doesn't look like there is.
No, not as drawn. I could put in one more bond and there would make it so there was resonance. Where would I put that bond?
On the third to fourth.
Yeah, exactly. Between carbon 3 and 4. So that would make it so that it is there is resonance. But minus that, no.
Okay. And then to the lone pair question, because I just had so when it refers to a lone pair, in the instance of oxygen, right? So if you I have a, let's say, just literally a plus charge, and then a line shooting out straight over to an oxygen, and then another, let's say, another bond coming off the oxygen.
All right.
If I'm counting localized and delocalized electrons, do I only count one or both? Is both? How would that?
Hold up. So I didn't quite get what you meant. Did you mean this?
No. So it moving the oxygen up where there's no double bond. So it'd be
an ether? Yeah, okay.
Yeah. So this guy here. Really need to start just using functional group names out loud. That way I can better remember them.
Totally. I mean, honestly, it's a whole. When you get to the end of this semester, you'll realize that you've basically learned a whole new language. But that's one of the things that I'm going to try to do is just use the language over and over again, so that hopefully, just by immersion, you guys get it. But yeah, absolutely. Okay, so then your question was, your question was this pair of electrons, if I'm going to draw my resonance, right, it's going to be this pair of electrons jumping into that empty p orbital. And then am I done?
No, because you need to conserve the positive charge.
Absolutely. So net charge over here is +1. That means net charge over here has to be +1. So that's going to go on the oxygen. And the one thing I think it's a little weird for people maybe to see why that would be the case. It's because this pair of electrons used to be all to oxygen. It had it all to itself. And now all of a sudden it has to share it with carbon, right? So that's sort of, again, you're thinking of movement of electrons and how charge relates to that. But yes, again, just double check being the net charge. Excellent. Okay. So sorry, what was your specific question about this example?
So referring back to like the like electrons being localized or delocalized.
Right.
There's technically no way of like pointing at one set of electrons and saying you're the one that moves, you're the one that doesn't. You just have to know that one of the lone pairs is definitely staying behind. So one of them will be delocalized and one of them will be localized.
Yeah, I mean, it wouldn't have mattered which one of these pairs you picked.
Yeah.
Right, because in the drawing it's arbitrary. But yes, this pair of electrons lives in a p orbital. That's why it's allowed to delocalize. This pair of electrons lives in an sp2 orbital, which is why it is not allowed to delocalize. So I think maybe one of the questions that the sort of question that I think you were implying was, it isn't all 4 of these electrons that I should consider to be delocalized. And the answer is no, it is not all 4 of those electrons you should consider to be localized, because a pair of them lives in the p orbital. That p orbital can delocalize. The other pair is sticking out in, this sp2 orbital, kind of poking out this way.
All right.
So that's where that hybrid orbital geometry lecture from last week is sort of important. Those bubble diagrams that I had, it's important to sort of like be able to like remember that back to that in your mind and see those p orbitals sticking out above and below, because there's something very unique about pi bonds and about delocalized electrons that relates to that sort of bubble diagram, those structures.
All right. The next question I had, is it potentially possible to have multiple different types of resonance happening to create a structure that would not occur if not having those multiple resonance happening? So in a good example of putting that in a manner that doesn't sound so convoluted is in those instances, right, where you said so if I have a structure over here that has resonance and there's a sp3 effectively separating the 2 groups, and then over here I had another sort of resonance. How is that drawn with multiple arrows on both sides of the molecule, or are they just? You're
talking about something like this?
Yes.
You have 2 resonant networks here that aren't connected to one another. So you could absolutely draw a set of arrows for this one. Sorry, it'd actually be this pair coming up here. And then you would have a different set of arrows for this one. And they would sort of mean 2 very different things because these networks aren't connected at all.
Okay. So then if the question came up, draw all of the resonance structures, would it be kind of A true, B true, A false, B true, A true, B false kind of thing?
It would be a cruel question, I would say, but just because it's a little complicated. But I guess really what you would have to do is make sure to draw every possible iteration of this molecule. So that includes the results of just, wait, let me call it 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
And I'm sure that is a bit of a, like, that'd probably be, if that sort of question existed, it would be more of like, this is the challenge question for a weak thing, similar like the structural isomers. Yeah. Like one molecule, find the structural isomers for one molecule instead of like 12.
Yeah, well, So, I mean, the important thing is that if you're going to really draw you want to think about it as a set. If you're going to draw, if I'm asking you to draw all the resonance contributors, there are a set of molecules that would all be considered to be the resonance contributors. So notice in this one, all I've done is bounce that blue network around and not the red network. I would have to do the same thing where I just did the red network and not the blue network. And then I would have to do one where I did both.
So that was pretty much the question. Like without having to sit here and watch you
and I think,
draw 50 structures.
Yeah, and again, that'd be mean. But I think that what you're sort of going at is this idea of you're drawing this set of statistically possible structures.
Yeah.
And you can weight each one with its sort of stability or its prevalence as far as it relates to the molecule. Yes, that's true.
Okay. Yeah, that's starting to make a lot more sense.
Yeah, right. So like if you went on in your organic chemistry career, you might be getting to the point where now you're going to run calculations on each one of these structures and then actually determine those percentages and all. That's obviously not what we're doing in this course, but that's sort of the building blocks that we'd be sort of building.
Yeah. Really setting up just a conceptual understanding, and then at a further date, if you continue on in OChem, actually putting like numbers to the methodology.
Yeah, and in your math, right? I mean, that's the other thing, is that chemistry sort of parallels math skills as well. So you like most people in the class, and I mean, just don't necessarily have the mathematical skills to be able to tackle that problem yet. So that would be something that would be addressed later in your education.
Yeah.
Real chemistry is hard math.
Yeah, I was joking around with Mr. Ragsdale, physics. About how chemistry and physics are this weird dichotomy of dual understanding, both like completely solidated in structure along the lines of math. Yeah.
And so much of chemistry, what we do is to try to avoid the complicated reality of quantum mechanics, because we can do a pretty good job, right? This idea that carbon has 4 bonds. That's obviously rooted in quantum mechanics, but we don't need to go and like draw Schrodinger's equations every time we want to talk about it. We could just say carbon has 4 bonds, and that's true. So it's oftentimes a game of simplicity in order to avoid the complicated truth.
All right. I think that's all. I think I'll be able to tackle this discussion work now.
All right. Yeah, just let me know if you have any more questions.
All right, I definitely will, and thank you very much, and for being available on the weekend. That was.
Yeah, no problem. All right, man.
Thank you.